Hello again, and welcome back to Advent of Code 2025 in MIPS assembly for the PlayStation 2. We are up to day number 7. Day number 7 is a pretty fun day, though not very difficult and not very long. So we've gone into the laboratories. We have found a teleporter pad. The only way out is teleporter. And it's leaking magic smoke, which means it's broken. Right? We have to check the tachyon manifolds or something like that. So there's a location where the tachyon beam starts and goes downwards in the pass free to empty space, but if it hits a splitter, the beam is stopped and instead two new beams appear. Right? So it hits the beam there, and you get two new beams on the other side. Right? And those go down, and they hit more, and you get two beams on either side, and it goes, hey, it makes three beams because there are two in the same place. Fine, that's fine. And then it's like, hey, how many beams do you get when you get down to the bottom? Actually, what is this? It says, to repair that, you need to first understand the beam splitting properties is split a total of 21 times. Okay, so how many times do you actually hit a thing here, basically? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then over here is 21. That one there is not hit. So out of a possible 22 that were in here, 21 of them get hit. Which is easy enough, and the result, whatever. And then it's like, well, actually, what you need to work out is how many paths, how many total paths there are to the bottom. And in this case, if they overlap, that's still another path. So, yeah. You can end up on a lot of paths down to the bottom. I don't know the number for it. Whether you say it's exponential or it's it just goes up a stupendous amount of times. So even though the normal brute forcing kind of solution to it is very simple to understand, if you end up like trying to trace all the paths down, you're going to end up with trillions of paths, which takes a long time to solve. So of course the solution, as always, is buckets. It's always buckets, right? Your beams are going down all at the same rate. It's there, and then it's there, and then it's there, and then it's there. So you just go, well, I have, X number of beams in this position on this line, right? So when you get down to here, you go, hey, I've got one beam on this side in this position, and one beam in this position, and one beam in this position, one beam in this position. And then when it splits, when these ones split, you go, I've got one here, and I've got two beams here, and one beam here, right? And so whenever you get these things, you just add them together into buckets. You just add the beams together into buckets, right? Whenever they overlap, you add more into buckets, and that's how you do it down to get the part 2. So let's have a look at the code, what I've got here. Right, normal stuff. Got the input starting and the ending. I'm finding the width. 5 hex 5.3 here is that I'm looking to see where the start, the S, is, which is always in the first row, so you can always look for it there. That's fine. If it's not an S, then we go to check if it's the end of the input. I think it's always in the middle as well. That could have been another thing that you do. You just divide by 2 and add 1 to get the center of the thing to start from. Doesn't matter. Does not matter at all. So go through that, looping through across the width of the first line to find the width of it, so that I can move downwards, because again it's a grid problem with buckets, right? and you loop around that, and then I load the input text and I subtract it to get the width. So S5 has my start, F6 has the width, S7 has the end of the input. So that S7 is also going to be my check to see if I got out of bounds, sort of thing. Doesn't matter. And so what I'm going to do is I'm going to have two lists. And this one, movers and new movers. So S0 first. These are memory addresses. Where did I put them in memory? I've got movers here at what was it, 200,110 hex, and then new movers at 201,000 hex, which is, where is that in memory again? It's pretty far down. Where is it in memory? I can't remember where it is in memory. Doesn't matter. Doesn't matter. Here we are. Let's go back to where we are here. Right, running the solution. Blah blah blah. So I'm setting up the first movers first. The first movers first, yeah. So the first mover with the beam from the start. So I bring in the list beginning, load up a 1, I store 1 into there, which is the length of my list, right? I shift, logical shift left 4. Do a logical shift left 4 there, which is going to times it by what, 16 or something. Yeah, times by 16, doesn't it? 8. 1 is 2, 2 is 4, 8, 16. Yeah, you multiply by 16. Then I add add it to the start, to the movers here, and I store word S5, which is the start, into there. And then I store 1 with an offset of 8 into there as well, the same position. And then I load up new movers and I zero that one out. So actually it might help if I bring up the debugger here, so that we get an idea of what I'm actually doing. So I'll bring up the add this to the stage as well. I need a new window capture. This is right. Okay, bring this in. Right, so here's my debugger here. Here is the most of the input is on here at 20,000. And my new movers is going to be in here, right? So the first thing on the first line is going to be my list of my input length, or my array length is going to be in this first line here. Then each entry in my list, the first 4 is going to be, what is the first 4 going to be? I think it's like an ID. Is it an ID? No, the first 4 is going to be the X position, right? The X position in this line, essentially, right? Like on 0, 1, 2, can you even see that? You can't even see it. Let me move this out of the way again. Yep. Like 0, 1, 2, 2, 3, 4, 5. So at X position 5, there is a line, right? And then from 8, about 8 here, 1, 2, 3, 4, 5, 6, 7, 8, is going to be a 64-bit number, which is how many paths are on that line. Are there. right? So I'm using 16 bytes per entry. The first 4 bytes are the X position, and the last 8 bytes are the number in that line. So let's get rid of that again. Now we know how that's set up. And I'm going to alternate between these two lists, essentially. Then once we've done that, we jump into the beam solver, and then there's finish day down here. Right, that's the only thing that we do now. So we're in beam solver. We're only backing up one, actually one entry here, the RA. We've got Li is going, S0 is going to be movers, S1 is going to be new movers, and then we have this beam loop, and then beam solver end, and then we calculate everything, and then we've got the exit beam, and that's a one loop thing here. So we go into our beam loop, we load a word S2 out of S0, which is our movers. If there are no, so I'm checking the length of our list, right? If there's nothing in the list, if it's a 0, then we're done. But we shouldn't get there, right? This probably won't get hit. It's like this is just a fail-safe type thing. Then we shift it left 4, right, and add that 2. So we shift the length by 4, which multiplies by 16. Then we add the start position memory address to it. I should probably, no, d-adds doesn't need to be done. Ding dong. So that will send us to the last entry in the list. We'll start from the last entry and work our way back to the start. Slightly easier, I think, most of the time. We load a double out of S2. I'm kind of thinking here, why am I doing exactly a double? I've got S3 over here as well, which I haven't set up. Where's S3? Beam solver there. Where did I use S3? I didn't delete anything, did I? Oh no, wait, that's S3 is right there. I'm probably using a memory address for. Am I using the memory address for thing? S5. Yes, I am using the actual memory address for the X position, right? So for each of these lines that I've saved into my list, I've saved the memory position of that in my input, like down in my input down here, right? Wherever this ends up in memory, it's saving that whole memory position, not just an index on the line, which is odd, but it works. Who cares? That's fine, right? But then I load a byte. That is weird. So I load the double from S3, S2, 0. I mean, even this seems kind of weird. Oh well, who knows what I'm doing. Right. Okay, so I'm loading a byte from that memory address, right? From that memory address. So I want to see what I'm doing at this position. So what I do is that I have each beam, and then I move it. Well, I check where it is right now, like where it is, and then once I'm done, I add the width of the array to essentially move it down, right? and then I put that into the array. And then the next time I go through the loop, I check where it is, and if we're on a caret mark, then we'll split. So that's what I'm doing here, right? So I load the first beam thing, right? I load up the first beam. I load the byte from its position and where the beam is in memory in the grid. I check to see if it's a caret, OA. If it is, then we go beam row next. Then I also check to see if we've gone beyond the end of the input. If the beams have gone out of the input, out of the grid, then we're going straight to beam solver end. Wait, sorry, OA is the end of the input. Oh no, sorry, because the beams could potentially, in the case that one of these carets is right on the edge, it could spawn a beam that's on the new line character. So what I'm doing here is checking if I'm on a new line character and to ignore those beams, because if I go out of the grid, we'll just ignore it. I don't think that is actually in the input, but it's a check, right? Okay, so now here is where I'm checking for the caret, the 5e, right? So if it's a 5e, if it's not a 5e, then we just go beam down, right? We just move it down. If it is a 5e, then I load here S4 is going to be how many beams I have in my input here. Then I go load this OX7C. I'm quite sure I've got 7C in there. We might see soon. I store that byte into there. No, it can't be things. It might be the pipe symbol. It might be the pipe symbol. Yeah, I think it's the pipe symbol. Yeah, it's the pipe symbol, that's right. 70 is the pipe ASCII. So I load that. I add S6 to S3, which is my thing here. So what I essentially do here, I think, is that I go down to here and I actually spawn the two down here rather than directly beside it. For whatever reason, doesn't matter. So I add the width to it, and then I subtract 1, and then do add to movers. Then I store the pipe into that position, like down over here in the thing, and I do another add to movers, and then I do one on the other side, +2, so it goes on the other side over here, right? Jump to the add to movers, and I store another pipe there, and now I increment the silver res, because whenever we hit one of those carets, we want to do a silver res, and then we'll jump to beam row next. Right, and of course whenever we do a beam down, we need to add that to the new movers as well, right? Then we go beam row next. We subtract 16 from that pointer because we're going upwards through the array that we're looking at, and if we haven't reached the start of the array, then we go back through the loop. And once we have finished going through this array, we go to this JL switch movers, and then we jump back to this this beam loop to start this up again. So once we are done, once we've made it to the beam solver end, which means we have to, no, actually we have to always get beam solver end, which would be one of these ones here, or potentially this one here. Right, then we count out the contents of our buckets. We go through the array, whichever array we're in, which will be S0. I'll get onto that in a second. And we just count how many are in each, right? This is a safety thing here. If there's a 0 length, we just bail out, because if we go into this count golds without a 0 length, it will screw up probably. Count all the way through memory. We shift that times by 16, of course. We add it to the starting here of the array length, and then we count through it, loading doubles out of the second part here. And we add them on using d-add, because it's going to be a very big number. And we move that pointer and until we get to the end of it, and then we store the gold back into there. And then beam exit, we're going back to the finish day, back to over here. Alright, so what have we got? The switch movers. Okay, switch movers, because we had S1 was S0 was movers and S1 was new movers. So what we do is that we just swap around the contents of S1 and S0, right? We move S1 into S3, we move S0 into S1, and then move S3 into S0. And then we go back. And we store 0 in the S1 position, which is the new movers, right? Which is, well, we say it is the new movers, but we just swapped around which array we're pointing to, right? So, and then we've got add to movers. So what we need to do here, I back up a few more registers here. We load in the length of new movers. So we need to, whenever we're adding a new beam, right? We need to see if that beam's going to be overlapping another beam. And if it is, then we have to add their contents together. Well, we don't want to add a new value to the array, a new entry to the array, but we want to add the contents of that previous beam to the current beam, so that you add them together, right? So if you have, say we're looking at this point here, if you have 5 beams here and 6 beams here, you end up with 11 beams here, and then 5 on this side and 6 on this side, right? You want to add them together. So yeah, so you want to go through, this side here gets evaluated first, so you end up with 5 in this position, and then the side here gets evaluated and it adds 6 into this position, right? So I'm going to go through here, going to loop through the movers, looking for this memory address in the list already, right? If I find it, the same memory address, it's equal to, right, we've got S3 is the beam address, S4 is the number of beams. If it's the same as the address that's already in the list, we add to add exist mover. Otherwise, we'll end up falling out of this into add a new mover, right? And so we increment the index, or increment the length of the list, the array. We store it back. We go to the position of the new index. We add that to the length of the array, whatever. We store the memory position of the beam, and we store its value, and then we go add movers end to jump over this add exist mover. Otherwise, we load out the existing movers number of beams. We add the number of beams from this one, and then we store it back in, and we fall out, right? And that's it. That's all the code. It's not very long. It's not that complicated. But let's bring up the PlayStation 2 emulator, PCSX2, and unpause it and run it. And it's done. Takes no time at all. Very fast. And we can see, if I scroll to the right place, that my answer is correct, 1605, and something very large down here. So That is correct, yes. Yep. Alright, so that was day 7. Might actually bring up, where are we? Bring this here up again, and we can just have a quick little squiz at this, look at this memory again, right? So we've got our results over here. The silver, gold result there. Here our length of this array is 5A. I don't know how many that is. These are these memory addresses of where the beams were, or beams are, at the end. At the end, I think. See, at the very, very sides of the output. If I get rid of this for a second, move this over here, right? At the very edge out here, you have like one beam, right? And then over here somewhere you've got 4, 3, right? Then it builds up, and then in the center you end up with this massive amount over here, and then it goes back down over the other side. Right? So that's that first length there. That's the first array. And the second array should be down here at whereabouts. There it is. And you can see it's missing the length because I cleared off that length when I switch back to the other array. And so this is the old data which is just sitting in there and would be written over in the next round, if there was a next round. But it's over. It's finished. Alright, so that is all of day 7 now. So, next one, day 8. Day 8 is probably going to be the coolest of these solutions. And I hope you're looking forward to it. Until then, see you next time.